In the previous lecture, we had discussed the basics of information transfer mode, and we had seen that historically the circuit switching was one of the first information transfer mode which was used for the telephone networks. Okay. Now, circuit switching is more efficient for the transport of real-time services which require quality of service guarantees in terms of delays and loss. Essentially, the time division multiplexing and circuit switching offers almost no delays except for switching latencies and no packet losses. But on the other hand, circuit switching was found inefficient for the transport of bursty sources. Then we saw that for the bursty sources, the transport mechanism that was developed was called as packet switching. While packet switching is efficient for the transport of bursty sources, but it offers no quality of service guarantees. Okay. It is essentially a best effort switching technique where the network will make every attempt to transmit the packet, but it offers no quality of service guarantees in terms of the delays and the packet losses. ATM switching was, or the fast packet switching as it was called, was developed by merging the concepts of both the circuit switching as well as the packet switching. Okay. It has the advantages of circuit switching in the sense that it offers certain quality of service guarantees, okay, just like circuit switching, but at the same time it has the advantages of packet switching in the sense that it offers you the statistical multiplexing gain. Now, how both these characteristics can be combined into our packet switching node with quality of service guarantees, that is how you can give the quality of service guarantees by at the same time by doing the statistical multiplexing. We had seen in the previous lecture with an example where we said that let us assume that there is a packet switch node which has say 1 to n input ports and 1 to n output ports. Okay. And now these input ports, these traffic sources which are transmitting on 1 to this input port, so this is essentially a stat mux. Now, each of these input sources may be having the data rates which are denoted by Ri, R1 plus R2 plus so on till let us say Rn. Now, we want that these sources, when they are multiplexed, okay, their combined output transmission rate must be less than or equal to the output capacity which is R. Okay. Now, let us say that this Y, which is the combined transmission rate of R1 plus R2 plus Rn. So, what we want is that the sum of these transmission rates must be less than or equal to the channel capacity or the link maximum bit rate of the link. Now, we had seen an hypothetical admission control mechanism where we assumed that each source knows its traffic characteristics in terms of its probability density function. So, each of these sources can specify its probability density function to the network. Now, if the network knows the probability density functions of each of these Ri's, that is, if the network knows the probability density functions of each of these Ri's, and let us denote them by FR1 R1, FR2 R2 and FRN Rn, then we know that the network can compute the probability density function of Y, which is FYY. Now, if the network computes the probability density function of the output Y, then from this probability density function the network can determine what is the probability that the combined output rate y will become greater than r, okay, and whenever the combined output rate becomes greater than r, there will be a packet loss, and if there is a limit on the tolerable packet loss, let us say delta, then we need to ensure that the probability that y is greater than r is less than or equal to delta. Now this is, as I pointed out, that this is a hypothetical admission control mechanisms, okay. Each traffic source invariably cannot specify its traffic characteristics through its probability density function. It may be possible only for offline stored video sources, let us say, which can be characterized a priori and their probability density functions are known, but certainly it may not be possible for the online traffic sources. Now one approach could be that if we assume, let us say that this y is r1 plus r2 plus rn, or let us say it's rm. Now if we assume that if we do not know the density functions of each of these ri's, okay, and if the sum of these traffic sources is very large, then we can also assume that y may have a probability density function which may look like a Gaussian probability density functions. So we can assume that this could be a normal or Gaussian probability density function. Provided the number of sources to be multiplexed is large. Okay. Now since the Gaussian probability density functions can be completely characterized by its mean, let us say mu, and variance which is sigma square, okay, then in order to determine the probability that y is greater than r, all we need to know is what is the mean of y and what is the variance of y, and this can be done by making online measurements on the traffic sources. So one of the simple admission control mechanism could be that the network first admits the users based on their peak rates. Okay. Let us say that there are no users in the network. The first user comes and specifies its peak rate. The network determines whether by admitting that user the packet loss requirements can be met. Okay. The user admits it. Now the second user comes. Okay. The network can do the admission control based on these peak rates. Now as the sources start transmitting their data, the network can make an online measurement of the traffic sources and can estimate what are the mean and the variance of the combined output rate y. By determining this mean and the variance, the network can determine that how many more number of users can be admitted into the network such that the probability that a combined output rate y is greater than the maximum bitrate r is less than or equal to the specified tolerable limit, which is delta. Okay. Now obviously these kind of techniques are called measurement based admission controls. We will deal with them in more details later, but here I just wanted to give you a glimpse of how on the one hand in the circuit switching technique where each connection is given a certain time slot in a time frame and gets a reserved bandwidth on the one hand, and therefore he is offered complete quality of service guarantees, that is on the one hand, and on the other hand in a packet switching network where there may not be any admission control, all the users are simply allowed to transmit, and whenever the combined output rate increases, okay, the link rate, then the packets are buffered. Okay, this is on other extreme. We have seen that how we can combine, okay, a combination of these two techniques, that is the circuit switching and the packet switching, at the same time and still offer, you know, quality of service guarantees. Now remember the hypothetical example that we just considered, where each source specifies its probability density function and also specifies a certain tolerable packet loss. This will degenerate to some kind of a circuit switching technique if each source specifies that its packet loss requirements is 0 packet loss, okay, if it does not want any packet loss. Then in that case, the only way in which that can be ensured is by admitting the users based on their peak rates, that is their worst case scenario. Okay. So this kind of statistical multiplexing technique, which offers quality of service guarantees and which we just discussed, can degenerate to a circuit switching technique, okay, if the quality of service requirements are 0 delay and 0 loss. On the other hand, it can degenerate to a packet switching technique, okay, where there are no constraints in terms of the quality of service requirements. Okay. So we have just seen how we can combine the advantages of the circuit switching technique as well as the packet switching techniques. Now remember, a statistical multiplexing which offers quality of service guarantees has to have some kind of an admission control mechanisms, okay, and the associated signaling procedures for that. Now before we go into the details of how this admission control can be done in practice, because as we have seen that the source cannot specify its probability density function, so how we can do that in practice, we will just look at this and how the ATM has come up with this concept. But before that, I just wanted to tell you some more differences between the circuit switching and the packet switching. Now consider, for example, a network of nodes which are essentially the circuit switch nodes. Now if you look this as a network of circuit switch nodes, and we have seen that each of these nodes, okay, could be a switch with 1 to n input ports and 1 to n output ports. On each of these links you have a TDM frame where you may have 1 to m slots, and these slots may get repeated. Now here you can see that a user number 1, let us say, is given a slot number 1, then that user is completely identified by its slot number. Okay. So the circuit identifier in a circuit switching network is a slot number, right. Now each user has been given, let us say, a designated slot, and he is allowed to transmit its bits in that slot of every frame. Okay. So let us say a user number 1 has been given slot number 1, then he transmits its bits in the slot number 1 of frame 1, then slot number 1 of frame 2, and so on. Now at the node we have, as you have seen, there is a signaling table, and that signaling table will tell you what is the input port. Okay, so this may be an entry of what is the input port, what is the input slot, what is the output port, and what is the output slot, and thus the bits can be switched from one input ports to one output port. So in a circuit switching, a circuit identifier is essentially a slot number. Now let us assume that this is a network of a packet switching nodes. Now how the things will be done in a packet switching? Now let us say again we have a network of nodes, but this time this is not a circuit switch node, but this is a packet switch nodes. Now In a packet switch node, there could be still a switch of 1 to n input ports and 1 to n output ports. But on this link, now you have the statistical multiplexing instead of the time division multiplexing. So if you expand this link, we will say that there may be 1 to m flows and they are being statistically multiplexed here. Now since it may be possible that the combined output rate may increase this, you require some kind of a buffer. Now moment you require some kind of a buffer, the bits of each of these flows must be distinguishable. Now how do you make a distinction? Typically you will make a distinction by encapsulating this data with some kind of overhead bits, which we call it to be a header. Now here on this node there will be a scheduler right here, which will look at the header and then it will schedule those packets. Now in packet switching, there are two ways in which the packets can be forwarded. One is we have the datagram switching or datagram routing. Second is virtual circuit switching. Now what is done in the datagram? Now datagram is quite similar to the concept of a postal switching or postal routing, where the postcards are routed. Each postcard or each letter in the post office is required to have the destination address. So quite similar to that, here in this packet where we have the data here, the header will have the destination address. The node, the packet switch node, looks at the destination address and then determines where the packet needs to be forwarded by using some kind of a routing algorithm. Okay. On the other hand, in virtual circuit switching, a virtual circuit is first established between the source and the destination before the data transfer can begin. So a virtual circuit is first established between source and destination before the data transfer can begin. Now this is very similar to the circuit switching, where a physical circuit needs to be established between the source and the destination before you can transfer the data. Now in circuit switching, when you are establishing a physical circuit, remember that we need to see, when you are establishing, this is a circuit switching, when you are establishing a circuit between this source to this destination, we need to see that the time slots are available on each of these nodes. Certain portion of the bandwidth therefore must be available on each of these links between the source and the destination. And if any of these time slots are occupied, or in other words, if the bandwidth cannot be allocated, then the call is blocked. Now on the other hand, if it is to be a virtual circuit packet switching, then we need to set up a virtual circuit quite similar to the circuit switching between the source and the destination, okay, but the bandwidth may not be allotted permanently, or the bandwidth may not be allotted to the circuit, okay, in any fixed manner. Essentially, virtual circuit is likely to exploit the capabilities of statistical multiplexing. Okay. Now, whenever we do this, whenever the virtual circuit is first established between the source and the destination, then the packets need not contain the entire destination address, but they may just have to contain, okay, the virtual circuit number. Typically, the bits which are required for the virtual circuit number may be much less than the bits which are there for the destination address. Remember, destination address will refer to all possible addresses of all the possible nodes in the networks, and therefore the overhead bits which will be required to represent a destination address will be much larger. On the other hand, the virtual circuit signifies essentially a flow between the source and the destinations, and may be called, okay, only when the call needs to be established. Moreover, as we will see later, that this virtual circuit number space can be reused also on some other links. Okay. So, as a result, typically the overheads which is there in representing a packet with a virtual circuit number is far less than in a datagram packet. But of course, the disadvantage is that in a virtual circuit switching, a call must first be established, or a virtual circuit must first be established between the source and the destination. Now, remember of course that for virtual circuit, a physical circuit must be there, because after all, when we transmit the packets, okay, it will consume resources of the link. But the circuit is called virtual because it consumes the resources only when the actual data is transmitted. Unlike in the circuit switching, where the resources may be consumed by the particular connection, even though it may not have some data to transmit. Okay. Now, as we were just discussing the statistical multiplexing with quality of service guarantees in the context of ATM network, an ATM network essentially is a virtual circuit network. An ATM network happens to be a virtual circuit network. So, let us see what are the key features of the ATM network. So, we will see asynchronous transfer mode, which we call it to be ATM networks. So, what are the key features that we have just studied? So, we say that it is connection oriented network. By connection oriented, we mean that a connection must first be established between the source and the destination. Okay. Then it is virtual circuit switching. And third, it offers quality of service guarantees through admission control and signaling. These are the three key features of an ATM network or an asynchronous transfer mode, which is essentially a packet switch network with quality of service guarantees. I would say ATM was one of the earliest packet switching networks which offered quality of service guarantees. Now, remember the term asynchronous here stands for asynchronous multiplexing. Okay. What we are saying that the multiplexing, as opposed to the synchronous multiplexing in the circuit switching, multiplexing in the ATM is asynchronous. Okay. Essentially, it is statistical in nature, exploits the statistical characterization of the traffic, and at the same time it offers quality of service guarantees. There are some other features of the ATM networks also. One of the features of the ATM networks is that other features of ATM, one of the other features of the ATM was that it uses fixed length packets. Which are called cells. Okay. Now, why fixed length packets? The fixed length packet essentially simplifies switching and transmissions. Okay. That is why when the ATM network was first developed, it was thought that it may be better to have the fixed length packet in terms of the simplicity of the fixed length packets. And the question then is, what should be an appropriate length of the packet? Since ATM network was thought to provide quality of service guarantees for real time services, there is a trade-off between what we call as the packetization delay and the latencies for transmissions. Now, suppose there is an analog voice which we are digitizing it by sampling it. Now, if you sample and put each sample into a packet, okay, then of course our packetization delay will be minimal. But in that case, the overhead associated with each of these data will be proportionately larger. So, obviously what we would try to do is that we would try to put many samples into one packet so that the overhead, okay, associated with a particular packet will be smaller. So, there is always a trade-off between the packetization delay and the overhead. Obviously, if you want to reduce the overheads, then your packetization delay increases. Okay, your packetization delay increases if you want to reduce the overhead, and the latency therefore for the real time services increases. Okay. Now, therefore, from the point of view of latency, the packet size actually should be as small as possible. It also helps in, therefore not having any echo cancellation mechanisms. But on the other hand, for the data transmission for statistical multiplexing efficiency, the packet length should be as large as possible. Finally, it was decided that a packet length of 48 bytes should be considered for the transport of an ATM payload. We add 5 bytes of header here, and an ATM cell comprises of 53 bytes. Okay. So, an ATM cell therefore consists of 48 bytes of payload and 5 bytes of header. So, essentially we have 53 bytes of an ATM cell. Now, as we have just seen that since ATM network is a virtual circuit switching network, obviously these 5 bytes of the header must have some kind of virtual circuit identifier. Okay. They must have some kind of a virtual circuit identifier. Now, we will see that what kind of other fields are there in an ATM cell. Okay. Now, these virtual circuit identifier, okay, as I was just mentioning, can also be reused. So, let us see how these virtual circuit identifier can be reused. Now, let us see that you have an ATM network where you are establishing a virtual circuit from here to here, and some of the calls could be added from here as well. Now, if you want to establish a virtual circuit, suppose this call comes first and therefore this node has allotted for this particular call, okay. So for this particular call we can say that for this particular virtual circuit we have allotted, okay, the virtual circuit number 1 here, okay, and if the 1 was not available here, this might have allotted it to be a virtual circuit number 4. Similarly, if a virtual circuit has to be established from here to here, now this virtual circuit might have been allotted the virtual circuit number, let us say 2 on this, 2 may, sorry, 1 on this, 1 may on this, but since 1 is already used by this virtual circuit, it could be, let us say, 2 on this, okay, and it could still be 2 on this link. So what we are trying to say is that this same virtual circuit may have a virtual circuit identifier number 1 here and a virtual circuit identifier number 2 here. So this VCI is swapped from 1 to 2 on this link. So in other words, we can reuse the virtual circuit identifier space on different links, and we can ensure that by doing some kind of VCI swapping. Now in ATM, the virtual circuit identifier is 16 bits, and therefore the total virtual circuits that could be there is 2 raised to power 16. Now what it means is that total virtual circuits that could be carried on any link, you know, between these two nodes will be restricted to 2 raised to power 16. But that does not mean that the number of virtual circuits in the entire network would be limited by 2 raised to power 16. By using the principle of VCI swapping, we can increase the number of virtual circuits in the networks to several millions, except that a number of virtual circuits on a particular link will be restricted to 2 raised to power 16. So as we have seen, the key features of ATM networks are that it is connection oriented at the lowest level, number 1. Number 2, it has virtual circuit switching, and number 3, it has statistical multiplexing with some kind of assured quality of service guarantees, which will be done through some admission control and signaling mechanisms. So what does it mean? Since it is quite similar to circuit switching in the sense that it is connection oriented at the lowest level, it is quite similar to packet switching in the sense that it is virtual circuit with statistical multiplexing. So we can see that it has the features of both circuit switching as well as packet switching. Like packet switching, it has the transmission in the form of packets, however these packets are fixed length packets, but like circuit switching, it has some admission control mechanism or a call setup phase where it will be determined whether the assured quality of service guarantees can be given or not, and if the assured quality of service guarantees cannot be given, the call is blocked in a way which is done very similar to the circuit switching. So it has, you know, the features of both the things merged into one. So now let us see what is the format of the packet in a ATM network. As we said that in ATM network, the packet consists of 5 bytes of headers. So which you are seeing here, this is the 5 bytes of headers, and we have 48 bytes of payloads. So now if you see here, VCI, okay, here, which is a 16-bit or 2 bytes of headers, which is VCI. So VCI stands for virtual circuit identifier. Okay, VCI stands for virtual circuit identifier. Then we also have VPI. So I will shortly tell you what is VPI. So we'll just see what is VPI and VCI. Now the logical connections in ATM, they are called virtual channels. Okay, and as we just saw, these virtual channels are identified by a 16-bit virtual circuit identifier or the VCI number. Okay, virtual path on the other hand is a bundle of virtual channels that have the same endpoints. So virtual path is going to be a bundle of virtual channel that have the same endpoints, and that is being identified by this VPI number. So if you see in this 5 bytes of header, we have 16 bits of VCI, that is 2 bytes of VCI and 1 byte of VPI, that is virtual path identifier. And what is virtual path? Virtual path is a bundle of virtual circuits that have the same endpoints. Now why do we do this? If you see here, now let's look at here. Now if you see here that virtual channels, a path is set up before any cells are sent. So as we can see in this figure, a virtual circuit has been established, okay, before any cells or any cell transmissions takes place. So what happens is that the user first signals for some connections, okay, the user first signals for a connection with certain QoS attributes and with certain traffic characteristics. Now the network then, by doing admission control at each of these nodes, determines whether the call can be accepted or not. Now if the call can be accepted, then the network returns with a virtual circuit identifier number, VCI number, and then this VCI number the user has to use in each of his subsequent transmissions. So this VCI number will be returned by the network, okay, if the call has been accepted, okay, and in the subsequent transmissions the cells will be carrying these VCI numbers, okay. Now what is VPI? If you say VPI is, as we have said, is a bundle of virtual channels that have the same endpoints. Now by doing this, we actually have some kind of a simplified network architecture which will give you increased network performance. How? Because we can reduce the processing and short connection setup times. What we can do is that we can set up a virtual path between the source and the destinations by over provisioning of some resources. Then subsequent virtual channels which have the same source and destination endpoints need not have to be provisioned every time when that virtual circuit needs to be established. So as a result, what is done is that a VP, a virtual path, may be established a priori with certain reserved bandwidth, and whenever the requirement for a particular virtual channel comes up, then out of that bandwidth may be given to the virtual circuits as and when they keep coming. So obviously this has the advantage that it has reduced short connection setup, it has the reduced connection setup time or short connection setup time, but at the same time it has the disadvantage that we may have to have some kind of over provisioning. Now subsequently, if you are having a virtual path identifier number, then the switching which is done at the individual switches, that may be done by using virtual path identifier VPI numbers only. That need not be done through the virtual circuit identifier or the VCI numbers, okay. Now this leads to some enhanced network performance and enhanced network services. Now we have seen here, as I pointed out here, that this is the cell header format, and typically in a ATM node it is also called the cell header format at the UNI. Now UNI stands for user network interface, and this is the interface that exists between an ATM user and its and the network, that is the first connect point between the ATM attached node and the network. On the other hand, between two ATM network nodes, the interface is called NNI, or network interface, okay. This is a UNI which is between an ATM user and the network, and that is why it is called as the user network interface. Now there are some other bits in the cells, as you can see that there is a bit called payload type identifier bits, and there is a bit called CLP. Now payload type identifier will identify what is the kind of payload that is following this 5 bytes of header. Okay. So this 48 bytes is a payload after this header, and what is the kind of payload is signified by this PTI bit in the header. There is other bit in this header which is the CLP, okay, the cell loss priority. Now this CLP bit can be set to 0 if the cell has a higher priority. However, if it is set to 1, then the cell does not have the priority. Now in the event of congestion, those cells, you know, whose cell loss priority bits have been set to 1, they will be the first cells to be discarded. Okay. So if a source is not conforming to its advertised traffic contract, and then the network may take two actions. Either the network may drop all those cells which are not conforming to the advertised traffic contract. However, if a network has some bandwidth available, has some resources available, then it may take a lenient view and it may allow these cells to pass through, but it may put the cell loss priority bit to 1. As a result, what happens that if in the subsequent nodes the resources are not available, then those cells whose CLP bits have been set to 1, they will be the first to get discarded. Okay. So this is the reason why the CLP bits have been put. The other bits, if you see in this slide, is we have HEC. Now HEC stands for header error corrections. So these are this HEC bits is essentially a CRC bits over the other 4 bytes of the headers. Okay. The other 4 bits are GFC or generic flow control. I will discuss about this generic flow control later on. So this is the 5 bytes of headers which is attached to the data of an ATM user, and this constitutes then the 53 bytes of an ATM cell. Now as we have seen that in an ATM a protocol stack, so let me just show how an ATM protocol stack will look like. So if you look at the ATM protocol stack, then of course we have a physical layer, and we have the ATM layer. Now the physical layer essentially is media dependent. It could be copper or it could be optical fibers. Now what are the job of the ATM layer? The job of the ATM layer, as we have seen, is admission control, signaling, and switching. Okay. So signaling for virtual circuit routing, okay, switching, that is switching the cells at each of the nodes, okay, and admission control for quality of service guarantee. So all these jobs are done by the ATM layer. Then there is another layer which is called ATM Adaptation Layer. Or which is called AAL. So this is our ATM protocol stack. Now the function of the adaptation layer is really to adapt the applications to the ATM. Now since the job of the ATM adaptation layer is to adapt the applications or services to the ATM networks, there are as many adaptation layers as there could be services that, or the application types that could run over the ATM networks. So we will see that there is an adaptation layer 1, there is an adaptation layer 2, there is an adaptation layer 3 and 4, they have been now merged, and one of the other popular adaptation layer is AL5. So I will shortly explain what are the significance of these ATM adaptation layers for different services. Okay, but before we go and into these various adaptation layers and their basics, one thing I would like to say is that ATM networks has classified the types of traffics that can be injected into an ATM networks as one of the 4 types, and which I will just show you what are those types of the traffics which have been classified. These are the ATM traffics type. One is the constant bitrate traffic. Now this constant bitrate traffic is used for emulating circuit switching. Okay. As the name stands, it is a constant bitrate traffic. It is a traffic with a periodic constant bitrate. Examples of these applications are PCM data, okay, coming from the telephone, or a constant bitrate encoded video conferencing or television or video transmission data, which are constant bitrate encoded, PCM encoded essentially. Then the second traffic type is the variable bitrate traffics. Variable bitrate traffics can again be of 2 types, the real time Vbr or the normal Vbr or non-real time Vbr. Okay. Now the variable bitrate, it is the variable bitrate traffics, okay, which is of the most significance in the ATM networks from the statistical multiplexing point of view. Okay. What we say in the variable bitrate is that the real time source is encoded, okay, using some kind of a variable bitrate codec, okay, by using some kind of compression techniques, and as a result the data rate of the encoded stream varies in bitrate, and therefore and it varies in bitrate fluctuates in a statistical fashion, and therefore its traffic characteristics is more statistical in nature. So essentially it is for the Vbr kind of traffics where the statistical multiplexing comes into the pictures. So Vbr traffic is a traffic whose bitrate fluctuates with time, essentially because of the compression which is used in encoding, and it is also the traffic which requires the quality of service guarantees. Okay. So all the talk that we had done for the statistical multiplexing with quality of service guarantees essentially for the Vbr kind of traffic. On the other hand, the CBR traffic, the constant bitrate traffic, is also a real time traffic which requires quality of service guarantees, but since the transmission of the bitrates is constant in nature, it is periodic in nature, therefore statistical multiplexing gains cannot be achieved for the constant bitrate traffic. So for the constant bitrate traffic, the ATM network will degenerate essentially to some kind of a circuit switching technique. Okay, so it will be very similar to a circuit switching technique, and that is why we say that a CBR traffic will require some kind of circuit emulations in the ATM networks. There are other 2 traffic types which have been specified in the ATM networks, which is called, one is available bitrate traffics, another one is the unspecified bitrate or the UBR traffics. Now available bitrate traffic is quite similar to the bursty traffic which is used in the normal packet switch networks, Now this is the traffic which does not require any quality of service guarantee. The bitrate fluctuates much like Vbr traffic, so it is quite similar to the Vbr in the sense that it is also bursty, but it does not require any quality of service guarantees. So though it will have statistical multiplexing, but since it does not require any quality of service guarantees, there may not be any need of admission control, okay, in this case. Now when the Vbr traffic was developed, if the Vbr traffic has to coexist with the traffic which also offers quality of service guarantees like Vbr, and when ABR traffic was developed and if it has to coexist with services like Vbr and CBR kind of traffics, then it was thought that there may not be any bandwidth available for the ABR traffic if the network tries to be greedy. That is, it tries to allocate the resources only for the VBR and the CBR traffic, then the ABR traffic, that is the available bitrate traffic, may actually starve of the bandwidth. So then it was decided that in the ABR traffic, the users are allowed to declare a certain minimum transmission rate, a minimum cell rate, which is guaranteed. Okay. So the ABR traffic in that sense now also falls into some kind of a QoS kind of traffic, which is given a certain minimum cell rate. Okay. But though it is for the bursty traffic, it is not a real-time traffic like voice and video. Then the fourth category of the traffic which was defined was called unspecified bitrate, which is like data applications which are sensitive neither to the cell loss or the delay. So it is very similar to the bursty traffic which is carried today in the internet world or in the otherwise packet switch world. Examples are like email applications or file transfers and so on. So these are the various traffic types which have been standardized in the ATM network world, which actually signifies the kind of traffic characteristics which will be injected into an ATM network. So as you can see that we have a spectrum of traffic sources, okay, constant bitrate traffic, which is typically a traffic carried in the circuit switch world, to an unspecified bitrate UBR or ABR kind of traffic, which will be carried in a pure packet switch world which does not offer any quality of service guarantees. So we can see that the ATM provides a unified framework for carrying of these traffic types. On the one hand, on the one extreme, traffics which require stringent quality of service guarantees, to the other extreme, the kind of traffic which does not require any quality of service guarantees.